The year is 1232. The Mongol army has Kaifeng surrounded Minas, one of the largest cities on Earth, Minas, and the defenders are out of options. So they do something no army had ever done in the history of warfare. They lash bamboo tubes packed with burning gunpowder to arrows, and they launch them into the siege lines. The defenders call them fire arrows. We call them rockets. That's the first documented battlefield use of a solid propellant rocket, more than 700 years before the space age. Now fast forward 736 years to a test stand in the Nevada desert, where a nuclear engine fires continuously for 28 minutes straight. No combustion, no flames in the ordinary sense. Just liquid hydrogen routed through a fission reactor and blasted out at several times the exhaust speed of any chemical engine ever built. Same core idea as those fire arrows. Completely different physics. So today we're going through every major type of rocket: solid, liquid, hybrid, the quiet little thrusters that keep satellites alive, nuclear and electric. How each one actually works, where it's been used, and at the end, we're ranking them all. Welcome to Cosmic Doodles. We're starting with fire. A rocket, stripped to its essence, is almost embarrassingly simple. Throw mass out the back, fast. The vehicle goes the other way. Every engine we look at today is just a different answer to one question. How do you make gas leave the nozzle as fast as possible? The oldest answer is the solid rocket. Those Kaifeng fire arrows were burning gunpowder in a tube, and for centuries that's basically all a solid rocket was. The modern version arrived in 1942 when Jack Parsons at Caltech did something clever. He threw out the old double-base propellant and mixed asphalt with potassium perchlorate, an oxidizer, and a rubbery binderness, so the propellant could be poured, molded, and cast into complex shapes at scale. That single idea is the foundation of every big solid booster since. Here's the part that trips people up. In a solid rocket, the fuel and the combustion chamber are the same object. The propellant is cast as a solid grain with a hollow channel down the middle, often shaped, like a star in cross-section. You ignite the inner surface, and the burn eats outward. The shape of the hole controls the thrust over time, and once you light it, that's it. You cannot throttle it, you cannot shut it off. It burns until it's done. The Space Shuttle's twin solid rocket boosters are the masterclass here. Each one was 149 feet long, about 12 feet across, and weighed roughly 1.3 million pounds at launch, around 1.1 million of that propellant alone. Each produced 3.3 million pounds of thrust at sea level, and together the two of them delivered 71.4% of the entire stack's liftoff thrust. Their propellant was almost 70% ammonium perchlorate oxidizer and 16% powdered aluminum fuel. And here's the elegant trick. The forward segment was cast with an 11-point star-shaped channel, deliberately engineered so that about 50 seconds into flight, thrust dropped by roughly a third minus, right when the vehicle hits maximum aerodynamic pressure, so the engineers wouldn't overstress it, punching through the thick lower atmosphere. The grain geometry was the throttle, programmed in before the thing ever left the factory, and those boosters were the first solids ever designed to be fished out of the ocean and reused. So solids are powerful, dense, and dead simple. The catch is efficiency. We measure that in specific impulse, means think of it as miles per gallon for rockets, in seconds. The best modern composite solids top out around 296 seconds in vacuum. Measured the same way, in vacuum, a good kerosene engine sits around 339, and the best hydrogen engines reach 452. Solid rockets trade efficiency for brute simplicity. No pumps, no plumbing, no chance of a leak. You light it and you hold on. Which brings us to the machines that do have pumps and plumbing and a whole lot of ways to go wrong. Liquid rockets. March 16, 1926. A cabbage field on his aunt's farm in Auburn, Massachusetts. Robert Goddard lights a spindly 10-foot contraption he'd nicknamed Nell. It burns gasoline and liquid oxygen fed from separate tanks, it flies for 2.5 seconds, it climbs a grand total of 41 feet, and it thumps down 184 feet away in the cabbages. That is the entire flight. And it is arguably one of the most important 41 feet in human history, because for the first time, propellant was a liquid you could pump, meter, and mass crucially turn off. 16 years later, that idea had been turned into a weapon. The V-2, developed in Germany under Wernher von Braun, made its first successful flight on October 3, 1942. Burning alcohol and liquid oxygen, it produced around 60,000 pounds of thrust and carried roughly 725 kilograms of explosive about 320 kilometers. And on June 20th, 1944, a test V-2 climbed to 175 kilometers, (mina 109 miles, becoming the first human-made object ever to reach space. It's a genuinely uncomfortable piece of history. The doorway to the cosmos was kicked open by a terror weapon. Nearly 1,400 V-2s were fired at Britain between September 1944 and March 1945, killing around 2,750 people, most of them in London. The same engineering that reached space was, at that moment, raining down on cities. But the liquid rocket's real superpower is variety, and the peak of raw chemical muscle is the Rocketdyne F1. This is the engine that lifted the Saturn V off the pad and sent men to the moon. To this day, it remains the most powerful single-chamber liquid engine ever flown, 1,522,000 pounds of thrust at sea level from one combustion chamber. Each F1 stood 18.5 feet tall, weighed 18,500 pounds, and gulped RP-1 kerosene and liquid oxygen at 5,683 pounds every single second. 5 of them clustered under the first stage produced 7.5 million pounds of thrust. And across every Saturn V that ever flew, the F1 never once failed in flight. Now, the reason liquid rockets dominate is that you can tune the propellant to the mission. Hydrogen and oxygen give you the highest efficiency, meanest about 452 seconds, which is why the space shuttle's main engines burned it. Kerosene and oxygen, around 311 seconds, is robust and energy-dense, which is why it powers the Falcon 9's Merlin engines. Then there's the newest generation, methalox, methane and oxygen, around 363 seconds, chosen for SpaceX's Raptor and Blue Origin's B4. And a special category, the hypergolics mix combinations like nitrogen tetroxide and that ignite the instant they touch, no spark or igniter at all. That sounds like a party trick until you're deep in space and simply cannot afford an ignition system to fail. Hypergolics flew on the Proton rocket and on the Apollo service module for exactly that reason, reliability when there's no second chance. But raw propellant chemistry only takes you so far. The real gains come from how you burn it. The Merlin 1D reaches a vacuum-specific impulse of 342 seconds for years, the highest efficiency ever achieved by an American kerosene engine, with a thrust-to-weight ratio around 200:1. Its injector uses a Pintle design first flown on the Apollo lunar module's descent engine, the very engine that lowered astronauts onto the moon. And the current frontier is SpaceX's Raptor family, which became the first full-flow staged combustion engines to ever power a vehicle in flight. Here's what that name means. Older engines burn a little propellant in a pre-burner to spin their pumps, then dump that partially used gas overboard wasted energy. Full-flow staged combustion routes both propellants through 2 pre-burners, so nothing is thrown away. The latest version, Raptor 3, unveiled in August 2024, burns methalox at around 300 bar of chamber pressure, the highest of any production engine ever built, and produces 280 metric tons of thrust while hitting roughly 350 seconds at sea level. It is the most refined chemical rocket humanity has yet flown. So far, it's been all solid or all liquid. What if you split the difference? That's the hybrid rocket. You take a solid fuel grain usually a synthetic rubber called HTPB but instead of baking the oxidizer into it, you inject a liquid oxidizer, typically nitrous oxide, from a separate tank. Here's the payoff. Since the oxidizer comes from a valve, you can throttle it and you can shut it off. You get much of the simplicity of a solid with the on-off control of a liquid and it's inherently safer to handle because neither half will do much on its own. The most famous hybrid moment came in the Mojave Desert in October 2004. Spaceship One, funded by Microsoft co-founder Paul Allen, designed by Burt Rutan's Scaled Composites, used a nitrous oxide and rubber hybrid motor to reach space twice inside 2 weeks, becoming the first privately built crewed vehicle to do it. That won the $10 million Ansari X Prize and lit the fuse on the entire private spaceflight era. Its successor, Virgin Galactic's Spaceship Two, used the Rocket Motor 2 hybrid, producing 70,000 pounds of thrust. The ship versus Unity made its first suborbital flight on December 13, 2018, reaching 51.4 miles up. One of those motors now sits in the Smithsonian. Now let's shrink way down, because not every rocket is trying to escape a planet. Once you're in orbit, most of what a spacecraft does is tiny nudges pointing itself, holding in orbit, twitching a few degrees. For that, you use the quiet workers. The monopropellant thruster uses just one chemical, HOSF, most often hydrazine. There's no combustion in the fiery sense. You flow the hydrazine over a catalyst bed, it violently decomposes into hot gas, and that gas leaves the nozzle. Efficiency is modest, up to about 237 seconds, but these things scale from less than a tenth of a newton to over 3,000 newtons of thrust, and they've been the workhorse of satellite attitude control since the 1960s. One manufacturer alone, Ehai Aerospace, has flown over 1,100 of them. Hydrazine itself was first isolated back in 1887 and first used on a spacecraft in 1959. Even gentler is the cold gas thruster. There's no chemistry at all. You just store an inert gas under pressure nitrogen or a refrigerant like R236 Fe- and let it hiss out through a nozzle. It's the weakest rocket there is, but it's the simplest and most reliable because there's almost nothing to break. When NASA sent two briefcase-sized CubeSats called Marco to fly past Mars in 2018, the first interplanetary CubeSats ever, they steered with R236 Fe cold gas thrusters. Two little boxes, puffing refrigerant, relaying a lander's arrival from another planet. Now we leave chemistry behind entirely. Nuclear thermal propulsion doesn't burn anything. It flows liquid hydrogen through the core of a nuclear fission reactor, superheats it, and exhausts it out a nozzle. And the reason this matters comes down to a single number: molecular mass. Chemical exhaust is heavy, water is about 18, pure hydrogen is 2. Lighter exhaust leaves faster for the same energy, and that translates directly into efficiency. Solid core nuclear thermal reaches somewhere between 850 and 1,000 seconds, roughly twice the efficiency of the best chemical engine we've ever flown. This isn't a lab fantasy either. The NERVA program, run jointly by NASA and the Atomic Energy Commission from 1961 to 1973, built and fired over 20 reactor and engine concepts. In June 1968, the Phoebus 2A reactor roared to 4,000 megawatts for more than 12 minutes, the most powerful nuclear propulsion test in history. And that same year, one engine racked up 28 firings, including 28 continuous minutes at full power. The engine from our cold open. It worked. And finally, the strangest of them all, electric propulsion. Picture a thruster glowing a faint, eerie blue in the vacuum of space. Instead of heat or explosions, it uses electricity to strip electrons off a gas, usually xenon, turning it into ions, then flings those charged particles out with electric fields at speeds no chemical reaction can touch. There are a couple of flavors: the gridded ion thruster, which accelerates ions through charged grids, and the Hall effect thruster, which traps electrons in a magnetic field. Both reach a specific impulse of roughly 1,600 to 3,000 seconds, many times what any chemical engine can manage. The thrust, though, is almost laughably tiny. Think the weight of a sheet of paper resting on your palm. You could never lift off a planet with it. But it can fire for months, even years. NASA's Dawn spacecraft ran its gridded ion engines for more than 5 cumulative years of thrust, enough to slip into orbit around 2 different worlds on a single mission: the giant asteroid Vesta and the dwarf planet Ceres. No chemical rocket could ever afford that much burn. This is the tortoise Venus, and Dawn is the race it actually won. So let's rank them by what each is actually best at. For raw liftoff power, chemical wins, and the F1 is the king, minus 7.5 million pounds that never failed. For everyday utility, the liquid rocket, endlessly tunable from hydrogen to methalox. For simple, reusable muscle, the solid booster. For safe, controllable suborbital hops, the hybrid. For keeping satellites alive, the humble monopropellant and cold gas thrusters. For maximum patient efficiency, electric. And for the future, Venus, for cutting the trip to Mars roughly in half, nuclear thermal, with about double the efficiency of anything we burn today. From bamboo tubes of gunpowder over a besieged city in 1232, to a rocket that flopped 184 feet into a cabbage field, to the first machine to ever touch space, to footprints on the moon and next to Mars. Same idea every time. Throw mass out the back, fast. We just keep finding better ways to throw. Thanks for watching Cosmic Doodles.